So 3.4 is about derivatives as rates of change. So derivatives, everything about what became calculus was really used in physics. That was the main applications for it, and really about a rate of change more than anything. So, it's important that we understand how we can use that in some applications. So there is a formula that gives us a rate of change over a certain interval of time. So here's just a formula that you will see at times. So it's a formula you can write down. You'll notice that the derivative is in there. So it can be used to estimate the value of a function at a given value. It's an estimation. Sometimes they will call function things like this an approximation. There's one even that's called a linear approximation, and that all comes from the derivative. So it says to estimate the value of the function. You'll see here that we know that f of 3 is 2. We know f prime of 3 is 5. We want to estimate f of 3.2. So let's kind of gather some information here. So remember, this is f of a plus h is approximately f of a plus h times f prime of a. Okay, so we need to determine what's our a, what's our h. Well, 3.2, you might agree, is 3 plus 0.2, okay? So we're going to call our A, we're going to call 3. We're going to call our H that small amount we've added on, okay? So now let's plug the A's and the H's into here. So 3 plus 0.2 is approximately f of 3 plus h, which we called 0.2, times the derivative at 3. So all I did was take out the a's, put in 3's. I took out the h's, I put in 0.2. Okay. So f of 3.2 is approximately, now let's look back up in the problem. They told us that f of 3 was 2. So just replace it with its value. They told us that the derivative at 3 was 5. So just replace its value. So that's 2 plus 1, 0.2 plus times 5, is 1. That's 2 plus 1. We can determine that at 3.2, we are approximately at a value of 3. Now, it's just an approximation, and it's used if we know just a little bit about the function, but we don't know a lot about the function in general. So it just allowed us to kind of adjust, hey, if we add that 2/10 onto the function, what happens? And based upon the fact that that rate of change at 3 was 5, we could say that that 0.2 is just going to add a little bit on 0.2 times 5 to the function. So it's just a tool that allows us to estimate a value of a function. The ones that we're going to look at a lot is motion, physics applications. So remember that your s of t is your position function. If you take its derivative, we will label that derivative as v of t. That's your velocity. If you take the absolute value of that, so a velocity could have a positive or negative connotation. So it is more directional. But if you want the speed, if you just take the absolute value of the velocity, you'll get that. And then the next derivative, so if you take the derivative of either the velocity or the first derivative of our position, you will get the acceleration. Remember The words average rate of change is just a standard good old slope between 2 points. Average rate of change, you need 2 points. Instantaneous rate of change, you need 1 point, and you need the derivative. That's the main difference, okay? So if they say find the average rate of change at such and such X values, they're going to give you 2 points. If they say instantaneous rate of change, they are talking about the slope of the tangent. So we need 1 point information at a derivative. Okay, so you have to know that language. I've talked about it before. Normal slope is a slope of a secant or an average rate of change. Derivative is an instantaneous rate of change. That's why it's a slope of a tangent. It just touches the curve or the function at that one instantaneous point. So you have to know that difference. So let's take a look at, it says here, comparing instantaneous velocity versus average velocity. So again, you need to get into your brain that the word instantaneous is referring to a derivative, where average is referring to just a slope between those points. So we have this position function, s of t is negative 16t squared plus 64, and it's drawn here. And it says, what is the instantaneous velocity of the ball when it hits the ground? So we're talking about that spot right there. Now, instantaneous velocity when it hits the ground. Let's think about when it hits the ground. That would mean that negative 16t squared plus 64 would equal 0. The height, the position is the 0 mark. The height on the ground is 0. If you go ahead and solve that, you get that 16t squared is equal to 64, so that t squared is 4. So t is plus or minus the square root of 2. But we're talking about time, and I am not going to go backwards in time. So my answer would be positive 2. Okay. And they've given you that in here. You can see at time 2 seconds, we hit the ground. So what is the instantaneous velocity of the ball when it hits the ground? What they've actually asked you to find is what is the derivative at time 2. That's really what they want. The instantaneous velocity at time 2 seconds. So for part A, they want us just to find the derivative. And so the derivative of that is negative 32t plus 0. Now you can put the plus 0, it doesn't hurt anything. Feel free, if it helps your brain, to see all the parts of that derivative. So we're just going to find the derivative at 2. So it's negative 64. And because this is feet per second, it would be just that very thing, feet per second. Please include any units when you're doing these problems. Okay? Now, it says, what is the average velocity during its fall? Now, the difference between average velocity is, what is the point at the start? Well, at the start, at time 0, we are at 64. We finish the whole descent in 2 seconds. At 2 seconds, we are at 0, position 0. So this is the point 0, 64, and this is the point 2, 0. And you just find the slope at those 2 points. Well, the slope is just y2 minus y1 over x2 minus x1, the difference of the y's over the difference of the x's. Velocity should also imply to you that you're going to have a rate of distance over a time. And so that would be 64 minus 0 over 0 minus 2, or you could turn that. That's 64 over negative 2, or negative 32 meters per second. So the average velocity over the entire trip from the top of the, whatever you're dropping at that 64-foot height, to the time it hits the ground is negative 32 meters per second. Now, what does the negative tell you? The negative tells you that it's getting closer to the ground as it goes. If it was positive, it was going higher up. If it was negative. So that's why the absolute value of that 32 would just be your speed is 32. So we have an average speed of 32 meters per second, but the velocity tells us we are heading toward the ground. We're getting closer to the ground at the entire trip. So that's the difference kind of between that instantaneous velocity language and that average velocity language. Yes. Oh, it sure would be feet per second. Yeah, we were using feet. I'm sorry. So it should be feet per second. Yeah, I didn't just somehow convert it. Sorry. Okay. So here's another problem. And let's answer some questions about this particular position function. This one is in meters per second. It says find the velocity at time t. So the velocity is just the derivative of our position function. We know by now how to take derivatives, hopefully, and so it should be a quick one. It's just 3t squared minus 12t plus 9. So that's our velocity. At any particular time t, we can find that instantaneous velocity by just finding the first derivative, okay? Now, it says, what is the velocity after 2 seconds and at 4 seconds? So if they've just said at a one particular time, then that tells you that it's an instantaneous. Use that first derivative. So our velocity at 2 is just 3 times 2 squared minus 12 times 2 plus 9, or negative 3 meters per second. So at 2 seconds, it is heading downward. Let's do our velocity at 4 seconds. What's happening there? Well, 3 times 4 squared minus 12 times 4 plus 9 is 9 meters per second. So this particular particle is sometimes heading downward and sometimes heading upward. So it's kind of zigzagging up and down. So when is the particle at rest? Well, a particle at rest implies that our velocity equals 0 because it had stopped its motion. And so when you see a question like that, we're just going to set our first derivative, 3t squared minus 12t plus 9 equal to 0. Now, we hope, if everything is lovely, that our function is factorable, which would be nice. They are all divisible by 3, so that can help you kind of narrow down your factorization. That's t squared minus 4t plus 3, which does factor to be t minus 3 and t minus 1. So at time 3 seconds and at time 1 second, it would be stopped, okay? The particle would be at rest. Let's look at the next part. It says, when is the particle moving forward? You know how I mentioned at 2 seconds, it was negative. It's going backwards. It's going down or back, depending on what your line of motion is. And so it's moving forward when its velocity is positive. So what we're going to do is we're going to think, when is 3t squared minus 12t plus 9 greater than, let's go greater than 0. Now we know that it's 0 at 1 and 3, right? Okay, so let's make a little chart. You remember last year, I think near the end of the year, we talked about those little plus or minus charts for inequalities somewhere along the line. I don't remember when, but so at 1 second and 3 seconds. Now this is time, so we can't go back in time. We don't have a time machine. So we do kind of have a 0 stopping point. Now let's think about what happens at 0. So it's 0 here and here. We've already found that it's at rest at 1 and it's at rest at 3. Okay, at 0, if we plug 0 into our position function, remember our position function, our velocity function here, what's it doing at time 0? It would get a positive 9 value, so it's positive here. Now, what's the number between 1 and 3? Well, 2 is in there. So if we plug in 2 as kind of a test point, and if I plug it into my velocity equation, oh, we already plugged in 2, didn't we? We got negative 3. And then for part B, we plugged in 4, which is after 3, and that was a positive. Okay. So when is the function moving forward? Well, that would be the positive sections here and there. So we could say that from 0 to 1 second, it moves forward. And then from 3 to infinity, it's moving forward. Up or forward, depending on how it's laid out, okay? So that's a little bit about if the direction changes from positive to negative. Many times we just drop something, and so that motion would all be downward. Think about if you're standing at the top of a cliff and you throw a ball upward, there's a spot where it's positive until it reaches the peak of usually a parabola of some sort, and then it goes down again. Now, in part E, it says find the acceleration at time t after 4 seconds. After 4 seconds. So let's do our acceleration function. Now let's go back for a minute to our velocity equation. Our acceleration equation is just the derivative of our velocity. So let's find the second derivative of our position. Let's do it again. So the acceleration is just 6t minus 12. So all I did was take that derivative of that 3t squared minus 12t plus 9. Then I get an acceleration function. Now, it says that's the acceleration at time t, so that would be that first section of the question. And then they said, what is the acceleration after 4 seconds? So plug in 4. So that's going to be 6 times 4, 24 minus 12, or 12. Now, our entire problem has been in meters per second for our velocity, so our acceleration is meters per second squared. So that is a physics application which comes up a lot. So those are the type that we're mostly going to focus on as far as applications of our derivative as a rate of change. So those are kind of the most important types that we're going to see. Do we have any questions about that? Okay. I'm just looking where we're going here. So we'll do these next 2 examples just on position and velocity, and then we'll stop and I'll give you some time to work on those types of problems that are in the homework. And then tomorrow we'll talk more about some other applications of rates. Okay, so let's take a look at this one. It says a particle moves along the coordinate axis in the positive direction to the right. Its position at time t is given by s sub t equals t cubed minus 4t plus 2. We want to find the velocity at 1 and the acceleration of 1, and then we are going to use those values to answer the questions. Okay, so first, let's find the velocity equation. So velocity equation, remember, is just the first derivative. So that's going to be 3t squared minus 4. Now you could put 3t squared minus 4 plus 0 if you want. It doesn't hurt anything. Okay, so that's our velocity. And the velocity at 1 second is -1. And it did not give us units. So there you go. It's -1. Now they also set it to find the acceleration at 1. So acceleration function is just the first derivative of our velocity or the second derivative of our position. So that in this case, just take the derivative again. So that's just going to be 16. So that would be some unit of length per time squared. Okay, so that's our acceleration. Let's put that as a value of 1. When we put 1 in there, we get 6. Now, let's answer the questions. Hopefully we can answer these questions. At A, it says, is the particle moving from left to right or from right to left at time 1? Do you see how it has a negative there? So this means right, they're calling right the positive direction. So that means it was going backwards. So that means that it was going, instead of from left to right, it's going from right to left, right to left. So it's going that way. Okay. So that's what that negative velocity tells us for part A. Now, part B is a little stranger to wrap your head around, but this is the way I always think of it. If the acceleration and the velocity are the same sign, so if both are positive or both are negative, it's speeding up. If the acceleration and the velocity are different signs, it's slowing down. That's all you have to check for. Same sign, they're going to be speeding up because they're not fighting against each other. Different signs, they're slowing down. So you'll notice that our velocity is negative at time 1, but our acceleration is positive, so it's going to be slowing. And you can research more about that from your physics teacher, but that's the best way to kind of explain it as far as what we're doing. Okay, so that's a little bit about your velocity and your acceleration, a little bit more about that. Okay, let's do another one. So we have our position function. It says find the velocity equation. So our first one, it's pretty easy. Our velocity equation is just the first derivative of our position function. So it's just going to be 3t squared minus 18t plus 24. Now make sure you're understanding where that velocity function comes from. So I just took the derivative using our power rules. So this one became a 3t squared, negative 18t plus 24. Okay. Now, for part B, so this is very reminiscent of the first example like this. It says, when is the particle at rest? So that's just, when is your velocity 0? When is it stopped? Okay. So we're just going to set 3t squared minus 18t plus 24 equal to 0. Now, they're all divisible by 3. Take out a 3. Factor if you can. If you can't, you have to use the quadratic formula. This is factorable to be t minus 4 and t minus 2. 4 times 2 is 8, but adds up to the 6th in the middle. So at time 4, and this is, they didn't give us units for seconds, for minutes, for hours, who knows. But at time 4 and at time 2, the thing would be stopped. Okay, so that's what B tells us. Now let's take a look at C. On what time intervals is it going from left to right or right to left? So left to right, think about if I move from left to right along the x-axis, that's a positive movement. Right to left, I'm going backwards, that's a negative. So what's great if they forced you to find part B, we can use those values on the number line. Okay, so just put those values on the number line. Those are our zeros. And then, of course, it said right here, our time is greater than or equal to 0, which is the standard in any kind of physics application. So let's plug in some tester values, and we're plugging them into our first derivative, this velocity equation. okay? If I plug in 0, I get 24. That's positive. So initially, we are going in the positive direction. We are going from left to right, okay? Now let's plug in 3 into our velocity. If we plug in 3, we get 27 minus 18 times 3 plus 24, which is negative 3. We're going in the negative direction. And then from anything after 4, so let's plug in 5. 3 times 25 minus 18 times 5 plus 24 is 9. That's positive again. Now, very often, not all the time, don't guarantee it, but many times you will see that alternating pattern, plus minus plus or minus plus minus, depends, but that's pretty common. Now, you can't guarantee that depending on how the factorization is, but it is common, okay? So it says on what time intervals, okay? So it's going from left to right, which is positive, from 0 to 2, and also from 4 to infinity. And then it's going from right to left, so backwards, only from 2 to 4. Now, don't worry about sketching a pattern, but basically you can find the position. I'm going to show you how, but you don't have to do this. If there's a question about the drawing the pattern, feel free to skip that for now. But let's plug in some 0. Let's plug in 0, 2, and 4 into the position function to see where we're sitting. Okay, if I plug in 0, I get 4. So I start out at 4. And then at 2, I get, I will tell you in a second. I am now at 24. And then at 4, where am I at? Well, let me tell you. I am at 20. So if you want to sketch a graph, again, don't make this harder than it has to be. So at time 0, I'm at 4 feet, 4 miles, they didn't say. I'm at 4 units, okay? And then at time 2, I am now at 24 units. And that whole time I was progressing in a positive way. But then at time 4, I went backwards somehow and got to 20 units. And then for the rest of the life of the thing, I'm going to be going forward again. Okay, so let me kind of show you what happened. From 4, and you could even label this at, this is S of 0, this is S of 2, this is S of 4. Gosh, I keep putting a little thing when I don't need it. Okay, so at time 0, we're at position 4. At time 2, we're at 24. We've gone backwards. At time 4, we've landed now at 20. And then for the rest of our life, we are going forward again. So that's the kind of motion sketch that they're talking about. The path of the particle, go forward and backward, forward and backward. And there are some more, we could even make it a little more accurate than that, but that's the general kind of thing. So if you look down at your homework, I would start with especially this first one. And here's another, these ones here are about this top section, about your velocity and your position. So start with those. And then tomorrow we will talk more about some business applications, some biology applications, things like that. Okay?